Okay, so let's see. So this is the next part. Okay, so first of all, just small remarks about the two norms that we are going to talk about. One is, okay, so first of all, we assume that we are over real or complex numbers. And we assume that we have a column vector with m coordinates in the field F. And the norm, the P norm is this P norm. And P is between 1 to infinity. Now we have a matrix M by N matrix with real or complex coordinate. So first of all, what is the norm C1 infinity F? This is an operator norm from the space that has norm 1 to the space that has norm infinity, but actually there is a typo. I'm sorry. So this is C infinity 1 norm should be, and this is the right definition. I look at the maximum norm of the image of Cx in norm L1 at for X with norm infinity. Okay, so it can be also stated like that, maximum of this bilinear form. If you over complex numbers, you can take a bar. And also, it's not easy to show. It's not difficult to show that first of all, you can also reduce this one to be less equal than 1, and you take real part. Okay, so what is the Grothendieck norm? Okay, the Grothendieck norm is very similar to what we have here, but instead of epsilon I delta j bar, we are going to take again. Okay, so it's I should put Cij outside, but it doesn't matter. Here I will take this is the correct version. This is that you take the inner product of two vectors of xi and yj when they are in a fixed Hilbert space. So you can, if you want the maximum, you can assume that the dimension of this Hilbert space n plus n, because any n plus n vectors x1 up to xn, y1 up to yn, they span the subspace, and that's enough. But actually, we will see that it's enough to assume that it's the dimension of this Hilbert space is the minimum of n. Okay, so it's very easy to show that this norm C infinity less equal than the Grothendieck norm. Just choose each vector xi and yj to be just in one-dimensional space. Okay, next. So what is actually why? So there is so much interest in this Grothendieck inequality, and first of all, there was a big interest in functional analysis, where his inequality, Grothendieck inequality, or his paper, which was published in 1953 in Bulletin of Brazilian Mathematical Society of Sao Paulo, so obscure journal, and it was in French, and only after 15 years, it was discovered by Lindenstrauss and Perczynski, this from Poland, and the Lindenstrauss from Israel. So, and they show that actually you can solve many outstanding problems. And further after that, what happened is as follows: that you see, this is NP hard to compute, and it comes in many combinatorial problems. However, this one is easy to compute. By easy mean polynomial time if you want absolute precision, because it's SDP semi-definite problem. Okay, so why this is problem in SDP? Okay, so let's first of all take a matrix C and make it, let's say, self-adjoint. So it means over real is real symmetric, over complex is Hermitian by this trick. Okay, yes, it is by this trick. And let's assume that GLF, it would be the set of covariance matrices. In other words, it would be positive semi-definite matrices with a diagonal 1, which means that essentially it would be a product of a matrix A star with A, where each column is of length 1. Okay, and so then CGF is just half of maximum of real of trace of this one, and this is an SDP problem, and it has a positive definite matrices. Therefore, it is computed in polynomial time with absolute precision. Okay, so why the space can be assumed of dimension minimum n? Because suppose you have m less than n, and this is the subspace of at most dimension n, and you take orthogonal projection on this subspace. So xyj, it would be xi pyj, and pyj is equals to yj equals 1, and that's it. We'll just don't need it just to show you some simple application of Krivine inequalities. Okay, so as I said, this was a result of Grothendieck, that after several years he quit functional analysis and moved to algebraic geometry. But this paper in '53 is the most famous paper, the most cited paper of Grothendieck. So this inequality is obvious, but that was the whole point of Grothendieck inequality, is that this SDP problem, this is bounded by some universal constant and this infinity one problem. So in other words, this would be an upper estimate of this NP-hard problem, and the difference is by some constant. Okay, so what is the value of the constant? Now this is the known value. This is actually by several authors. I forgot now the name was the one, but one of them was Asaf Naor. But there were some other government actually was showed that you can, instead of this inequality by Krivine, you can actually take it inequality or minus epsilon, when epsilon, God knows how much is that. Okay, and this inequality was proven, the upper bound was proven Hagerup, very nice paper, as you expect from Hagerup, and this one is just an example. Okay, so its application in Banach spaces, combinatorial optimization, quantum information, C-star algebras. Okay, so sometimes in, let's say, in quantum information science, you need to add, you want to restrict the dimension of the Hilbert space to D. So if you restrict D equals 1, you're going to get this norm, or again, infinity 1 here, but you can restrict to D. But so this is from physical meaning, that's very obvious that you want your experiment taking some Hilbert space of dimension D. However, you are facing the same problems that it is NP-hard to compute. Okay, you have similar inequalities as okay, let's see, similar inequalities as here. Okay, okay, yes. So let's see. Okay, so let's say the wonderful signals was discovered by Tillotson in 1980. That actually he gave interpretation of Grothendieck inequality as a maximum let's say violation of the Bell inequality. So let's explain this briefly. So we have here a system that emits photons left and right, and here is Alice and Bob, and they measure, oops, sorry, let me go back. They measure these photons, and they also can move, let's say, the apparatus. We'll see in a minute about this famous example from 1969. And so now, what is the Bell inequalities? It's say, okay, so we are going to go like Einstein, Podolsky, and Rosen. We are going to do hidden variable model. Okay, so if you do like hidden variable model, then you have Zij, because it has xi lambda yj, so it's expected value of two random variables which take values plus minus 1, because this is the photons is the left or right, plus minus 1. Okay, so then therefore, if you think carefully, then the maximum possible value of this experiment is going to be this norm, infinity 1, because you have to choose sort of, you will concentrate your concentrated value of random variables at all those points at which it is the maximum of at which the maximum of this norm is achieved. Okay. Now, what about quantum mechanics? Okay, so you have then you have, instead of this one, we're going to have trace of xi yj times rho. So rho is your density matrix you don't know. So you assume that xi yj is a commute. Okay, why? Well, because otherwise, you know, it would be more difficult to see who is before the first one, the second one. And assume that the square is equals like that. Okay. Now, so now you would like to take maximum of that. If you want maximum of that on all density matrices, it's enough to take it maximum on the pure state. And then you take your state and you multiply trace of this one, you shuffle to here, you shuffle to there. Now, if you think carefully, if this is a very so you can assume that you can normalize because the commute yx and z are actually the diagonal matrices. Let's talk about finite dimension, plus minus 1, plus minus 1. But the dimension is very big, and therefore you can think that essentially that this is, you can have almost arbitrary vector here by j and xi. And so therefore this is it. Okay, so let's see. So this is a famous Clauser-Horn's Shimony-Holt experiment 1969. So it was before, of course, before Thurso. And this is how it goes. So you have Alice ball. So here is essentially when you go to Alice, you have two ways. You know, it's reflected either in one way, it's a photon of the other way, and here is also in the other way. And voila, if you see, it's given by the Hadamard matrix. Okay. And now let's see. Now, so what is the H infinity one norm here? Essentially, you multiply that by 1 or minus 1 vector, and you see it's very easy to show, it's 2. Now, what is the Grothendieck norm? Okay, I'll tell you later, but the Grothendieck norm of orthogonal scale matrix is the sum of its singular values. But this is the singular values of the Hadamard matrix are of 2 by 2 square root of 2. So this is. So it's the bad valuation. I think these guys already figured out, but I didn't have time also to look at their experiment, but I think they maybe figured out was square 2. But now you see there was this famous paper of Friedland that shows that if you look at the Grothendieck constant for 2, this value is square root of 2. So therefore, for 2 by 2, it's a miracle that sort of you have a very simple matrix, Hadamard matrix, for which the maximum value, for which the bell valuation is maximum possible according to this model. Now it doesn't happen more for, I think, unfortunately, unless n equals 2, or at least I don't know. Okay, so once we see this, I saw that maybe what happens if you take a tensor product of Hadamard matrix? So the standard Hadamard matrix. So and I think for Hadamard matrices of order 4, they're all equivalent. So let's do that. Now, this is still easy to do by hand. You see that the H2 of R must be equals 8. So you take a thing vector 1, 1, 1 minus 1, and this is 8. Now here the Grothendieck norm is the sum of singular values. Singular values here, each one 2, 4, 8. No violation of balanced equality for this one. So this is amazing to me. So in other words, for Hadamard matrix of order 4, if you do this experiment, there is no violation of Bell inequality. Okay, according to this model. So if you use this fact and you're going to use, let's say, higher to M, see, you just always have the maximum valuation. The maximum valuation is as for the case of this experiment that we had. You cannot go over square root of 2. I don't know about other Hadamard matrices. Okay, so if you take a non-negative matrix, then there is also, if let's say Aij is non-negative matrix, there is no cancellation. When you do them, there is no violation. No violation of the Grothendieck inequality. And you can do this plus minus 1. Okay, next. Okay, so how about numerical experiments? So in other words, suppose I take a random matrix, for this experiment. Okay, so is it going to be violation, and how big? And so it turns out that I will see from numerical simulation that we did with my former student Sam Core. It's the average violation is increasing and seems to tend to a limit. Of course, it won't be the Grothendieck inequality. So this is actually very interesting for people who wants to, let's say, to use some random matrices. Okay, so let's expand. So what you do? So what do? I take a random matrix. Let's say I generate it from simplicity, you can get from, let's say, normal distribution, each entry linear independent, but then I have to do, let's say, SVD, or I have to do Gram-Schmidt with that, and to take no, I don't have to do anything. I'm sorry, I'm confusing. Then I'm going to compute the infinity one norm. So up to 15. So it's essentially, you think it's 2 to the power 14 choices for the vector. So 2 to the power 14, it's how much is 2 to the power? It's like 16,000. It's nothing for the computer. So you can do. Well, I said, this is to compute the norm of. So okay, so maybe I skipped something. What is okay? So what is I showed you what is okay? I defined was GRC. Maybe I skipped here. So GRC is just you take the Grothendieck norm of a matrix and divide by C infinity one norm. Okay, and we always numerical experiments only for real, because for complex, I think it's a mess, but I don't know. Okay, so here is the result. So you just take your random number generator, generate a random matrix. We have the sample is 10,000, and just you compute the maximum Grothendieck. Let's say the maximum is Grothendieck ratio. Let's say look at that. So here for n equals 2, the maximum is 13289. But we know the best one is square root of 2, it's 1.4 something, because it's random, okay? The minimum is always should be 1. However, if you look down here, it means that you don't have 1 minimum. Of course, it's random. Now, so this is not so good. But let's look at the average. The average for 2 by 2 is 1.011. So there is a variation, and if you look on this standard deviation is 0.36. Now you start to increase n. So what happens? You see this maximum is going to go down, because and actually it's all false. The maximum would be should at least square root of 2, but you don't discover because it becomes very big sample. Now minimum is, as I said, it's always 1, but it's very close. Now let's look at the average. It's increasing average. And look at, let's say for 15, this is the standard deviation. It's decreasing. So it seems to me there is a concentration. So I mean, I wish I could prove it, but I mean it's another project. Too many projects and only one head. And okay, let's continue. So now let's repeat some remarks of what I said about C infinity in this one. This is the norm one. This is NP hard to compute. This is polynomially computable. Now, so what happens? So Grothendieck inequalities gives you the approximate. So you can also from the proof of the original Grothendieck proof and modify it. Actually, if you do right work, you also can pull out the approximate vectors. Not only you can pull out the inequalities, you can pull out sort of the vectors for which you can get this Grothendieck inequality, so you can get sort of Maxwell vectors. Maybe it will be clear later. Now, so next is the dual SDP characterization of that, because if you have SDP problem, then you have a dual, and because you have a positive definite matrix in your set, they're equal. And this is the dual of the Grothendieck inequality. So it's an infimous. So now if you take U and V to be vectors which have M and N, it doesn't have to be a square matrix. You do like that, you get this inequality. Then the Grothendieck norm is less equal the square root of Mn times let's say the operator norm. But if you use SVD, then you can show that the Grothendieck norm is greater than the nuclear norm of the matrix C. But for orthogonal matrices, m equals n, this inequality and this inequality constant. And that's how you prove what I told you. So in other words, for orthogonal or unitary matrix, the Grothendieck norm is just n. Okay. And so now let's concentrate on, what can you see, let's say numerically, when you do Grothendieck inequality to orthogonal group, like let's say the Hadamard matrix or everything is just orthogonally scaled. So, so as I said, this is for n equals 2, it's square root of 2 in the best. But what does it mean to have a Grothendieck inequality for orthogonal group? What it means is as follows, that, okay, let's see here. It is as follows, that n is very easy to show. I'll show you that this is greater or equal than this norm. But what it says that, but actually is almost n divided by the Grothendieck constant for the orthogonal matrix or for all of them. Okay, so why? Because take a vector with coordinates plus minus 1, it's norm square root of n. And this is greater or equal than cx1. If you do just Cauchy-Schwarz inequality, you get here. So it's very easy to show this one, but you see, for the maximum, it's very close. It's also amazing. So let's do the same numerical experiment for the orthogonal group. And now you see, okay, so now essentially you look at because you know what the Grothendieck norm is constant, and essentially it's I look 1 over Grothendieck sort of norm, I look at this, the 1 infinity norm divided by n. So this is supposed to be 1 square root of 2, it's a little bit smaller, but you see what you have. When you do minimum 1, supposed to be sort of where you would say have the maximum violation. And here it's close, the minimum grows, the average also grows, and this is so much. So in other words, my feeling is that if you have an experiment and you have Hadamard matrix of any order or orthogonal one, the violation of the Bell's inequality is smaller and smaller. So in other words, it's not good to use Hadamard matrices for evaluation of Bell inequalities. Okay, next. So now let's go to next thing. Suppose what happens if A is positive semi-definite. Okay, so S and F means a set of n by n matrices with A star equals n. I call them self-adjoint. For F real is real symmetric. For F complex is just Hermitian matrices. Okay, so Sn plus is just positive semi-definite. So how about this Grothendieck constant for Gn plus? Okay, so Nesterov in 1998 proved that this is actually by half. And Benthal and Nemirovsky and Rus in 2003 for complex, this is 1 to 0.7. So complex is always lower than this. So now, according to Pizier, which actually work on let's say, really good outstanding work on this Grothendieck inequality, he claims, I didn't check, but I trust him, that actually Grothendieck in 1953 already showed this inequality. But again, you have to understand he put it in a different language. And also he claims that his methods immediately yield that this is also true. Okay, never mind. So we know about this one. Next. Okay. So the next thing is weighted Laplacian. So weighted Laplacian is very important in graph theory. So if you have a adjacency symmetrics of the graph, so the weighted Laplacian would be minus a plus the sum of the degrees plus the on each diagonal are degrees of the of your graphs. Okay, so this is the definition of weighted Laplacian. You just assume that the entries of the matrix are of diagonal are non-negative, and the A1n is 0. Okay, so it's the same like for the regular graphs, although the weights of graph are just non-negative, let's say numbers instead of 0, 1. Okay, so what we show together with my collaborator Lek Hang Liam, that if A is this thing, then the the Grothendieck norm is less equal than 1 divided by alpha G W A1 infinity F. So what is alpha G, alpha R G W? This is the famous Gomans-Williams constant. So, okay, so maybe just, so what is the, you see, what is the famous Gomans-Williams constant? So you have a graph and you want to cut it to two pieces such that the number of edges that goes from one to the other one is maximum. That is that is called max cut. NP hard, okay? But they show that, you know, with some using some randomness, they show that actually you can find a cut which is only 0 up to 0.87567 from the maximum one. So it's again, and this is, so it's a Grothendieck inequality. And so let's actually show it like that here, but it is for certain class. Now, if you wanted to do it for complex numbers, then it's slightly higher. Okay, and of course there is there's famous, I think, what's called the conjecture about quantum games that this is best possible. So I think NP hard or something, everything. Yeah, this is the best possible concept. I forgot about this quantum games conjecture, a unique game conjecture, I think it's called. It's to show that this is the best possible approximation. Okay, next. Okay, so now let's look at another class of matrices. This is going to be, let's say, what we call positives. It would be diagonally dominant. So AI equals sum of this one, of the sum of the rest of the norm for, let's say, and you take absolute value. So of course, the weighted Laplacian is a very subcase of that, because then it's all Aij non-positive and it's equals to. So then we show together with Leck and Lim that this is greater or equal. So this is the Grothendieck sort of constant. I'm not sure if this is best possible, but this is it. Okay. Next. Okay, so now we're switching the gears and we want to discuss an inequality, which is a Grothendieck type inequality for, let's say, for simplicity, it's called for symmetric matrices, but also can be Hermitian. So okay, so first of all, just a piece of notation, SNF0F is all Hermitian, or it's self-adjoint matrices is diagonal 0. So now let's introduce this one. So A gamma norm is not a semi-norm M gamma instead of Grothendieck G. It's maximum of X, the norm one, that you have a Ij Xi Xj. So this is like sort of like Grothendieck norm, but with absolute value here. And this is A theta would be small theta when you take here and restrict to one-dimensional subspace. Okay. Now, these are semi-norms. And why? Because if you take a diagonal metric with 0 trace, all of them would be 0, but these matrices are not 0. So you can quotient out if you want these norms, and you can assume that A actually has, on the diagonal, the entries are all the same. So then it would be a norm on this subspace. Now, you can also do another one, which for Grothendieck norm are the same, but here are not. You can assume that A gamma, capital gamma, is the maximum when each Xij is into norm is equals to 1, and the same expression. And A theta is the same for one-dimensional. So these are true norms. Okay. And so what we showed is that together with in this paper with Leck and Lim, so it's on archive, and we are submitting it. It's okay, and so we show that we have Grothendieck type of inequality, A gamma of F is equals Kf gamma A theta, because this is because A gamma of F is greater or equal, okay, and the same one inequality. Now, some people say, well, if you don't care about constant, then essentially, okay, I'll show you later. But what we were able to show that, and this is maybe not the best thing, that first of all, we have this inequality. So K Grothendieck is less equals than K gamma, capital gamma less K gamma. And those are the bounds. This bound is actually the original Grothendieck bound for Grothendieck norm. That's his bound from his paper in 53. This one is okay. This is a different one. Okay, this is for complex numbers. Okay, so now the claim is that this Grothendieck inequality is a special case of self-adjoint. Why? Because okay, so first of all, there's some small remark that if you take A gamma R and A gamma C, this doesn't change the value if you assume that A is real. And the same here, okay? Now, if you remember the trick, you from C like that, you introduce self-adjoint matrix like that, and then you can show that this AC small theta equals big theta equals twice the infinity of the standard infinity one norm, and this one AC gamma gamma is twice, and therefore we deduce that the Grothendieck constant less equal than this constant. Okay. Okay, so here is a lot of formulas which I had myself to look formulas to just explain. So now you can introduce the same the same norms when you assume that the Hilbert space is of dimension D. And so you have all these norms with D. I'm not going to go through all of that. And you have a so if you assume D equals 1, then you got the C infinity norms, and you have also this characterizations that A gamma D is equals maximum not possible D like that diagonal. Therefore, you deduce that K small gamma is the biggest one. Okay, and you have this inequality. It doesn't matter. Okay. So now again, I said that essentially you can so what happens that for D, if you have A is of dimension fixed n, then for D smaller than n, we believe for D equals 1, we know that this is NP hard, and for D greater than E, it's just polynomial computable. So, okay, and so that's it. Okay, next. So now here is a very nice sort of observation. So suppose you take A gamma D. Suppose you take, let's say, C, just for simplicity, C infinity norm of C, of real one. What does it, so what it happens? So what it's going to be the C norm of 2RD. This is going to be C norm. In other words, so the infinity norm with respect to complex number of a real matrix is going to be would be the Grothendieck norm for real matrices, but when you restrict the edge to be two-dimensional. Okay, so next. So you have all kinds of these inequalities with P. If you replace everything, dimension of the Hilbert space by P, you have similar inequalities. And so, as I said, this is the Krivin. This is he shows that this is equal square root of 2, and so this is the inequalities that we have. Okay, next. Okay, the next is it's a copy from Wiki. So just to tell you an idea, what is the value of these constants? Okay, so let's look. So what Grothendieck shows that this is is greater equals than pi over 2 because we computed what we now understand the Grothendieck constant for positive semi-definite. And this is, then Krivin had done many things about it. He first of all showed that actually it is equals to square root of 2. This is called lower bounds here, but it's actually equal to the log for n equals 3. For n equals 3 and 4. For n, he showed that, no, okay, that's the Krivin. Then Davis, I think when published, he shows that the Grothendieck constant is equal to 16670. And Fishburne, they show that this is lower bounds. So you invert it, so you see, it's all a little bit increasing, but not much. So this is the latest result. Next, what about the upper bound? So the upper bound, this is That's what the Grothendieck showed. Now, Ritz showed, but let's say Krivin did a lot of upper bound and actually conjectured that this bound that he found, it is the best possible bound, like that. And then Braverman in 2011 with a quite complicated paper, which I still don't understand, maybe didn't have time to look, but it shows that you can, it's not best possible, you can review by minus epsilon, but no epsilon, so that's it. Okay, epsilon is very good. Okay, next. Okay, so now there is a way, as I said, to compute the post-extended definite case. And this will give, if you compute the constant for post-extended definite case, as in Grothendieck case, you can do also lower bounds and you can have the limits. And this was actually this paper of Brouwer, Burman, and Tonner did. So they computed these inequalities for NEP, and and then they showed if you take for infinity, then you have the exact value. And actually, as I said, this is what Pizier calls the little Grothendieck theorem. In other words, positive semi-definite is much easier. Okay, so now let's look about symmetric Grothendieck inequality without absolute value. So then, in other words, what I want to find, I would like to find an estimate of the maximum trace of AX, and I would like to find an estimate of this problem, QA. So this is X Q less equal to N, and QA is that. This comes in many combinatorial problems, and it's NP hard. And then so now you say, okay, what we can do now, we're all smart and we do SDP approximation. This is SDP approximation. Okay? And this is for equal 1. So it was shown by Nemirovsky, Rus, and Terlaki that actually that you see that the SDP approximation of R less equal then is actually is less equals 2 log to N times Q of A. Okay, I think this okay, Q less equals N. So what is, and actually it was shown by Migreskin that this is that the order of the constant is 5. What does it mean? It means that if you don't take absolute values, there is no Grothendieck constant because it is increased by N. Now, what we showed, from our result, if you take maximum of Rn, R minus IA, this is less equal this quantity, which we don't know which of them is probably NPR. This is less equal than KR maximum. Okay, so to be more precise, let's define these two quantities. Suppose you want to know what we call a spread of this quadratic form in which x is from in takes value minus 1 into 1. This is the maximum and minimum. So this is the spread. And this is a stretch. And the spread is when you take the SDP approximation. So the stretch is equal to spread, but less equals than K gamma R stretch. Okay. Next. So actually now I think I have about 5 minutes. Let's.
We started a bit late.
Yes, I took it on. So okay, because I'm measuring. So okay, so I don't want to be cheated, for my time. 45 minutes, right? Okay. So how do we prove that? So how Grothendieck proved and how other people proved it? So what you should do. So let's explain a little bit for someone who's interested. So you start with the Gaussian distribution on let's say on matrices. Okay, each entry is independent Gaussian. Okay, and now if you have such a vector z from Fn, now here you define just vector define z divided by square root by the norm of z. In other words, you want to normalize this vector of length 1. Now, if z comes to be 0, it really doesn't matter because you assume that your order entries will be randomly distributed. So you can say, okay, you just call it to be just a vector 1, 0, 0. Okay, and now we take a unit disk. Unit disk, okay, in the F. So if it's for reals, it's minus 1, 1. For convex, is this one. Okay, and we are looking at a function from the unit disk to F. And this function is this one. It is the sign of ZU and ZV, because U and V are fixed, and Z now runs through all these matrices with Gaussian entries, and you take an integral of that. Okay. Now you it's not difficult to show that it has this expansion. For reals, for complex, you have similar expansion, but you have to be a bit careful here because it is x, the absolute value. So it's this function, although it's all for this complex, but it actually has real values because this is you won't take absolute value. Now you can do so the point is I think that this function has non-negative coefficient, the sum of 1, all of them. And here is the expression with the gamma function. And actually Grothendieck was the first one to compute, took slightly different, but it's the same, that phi1 area, just 2 pi divided by r sine x. And Hadamard computed, let's say, therefore C. This is his function, which can be written in terms of special f functions. Now, what happens about why is the difference between complex and real? And essentially, the constant over complex is less than over real, but Grothendieck didn't realize that there is a very simple proof for that. But it's okay. It was a great mathematician. Who cares? So here, let's say when Hadamard did it, you want to do, if you want to have his inequality, you have to take the inverse of this function. And the most difficult part of his paper was to show that the inverse of this function has first, let's say, first BK, first Taylor coefficient, it's odd function, positive, and all other are non-negative. This is very hard. I mean, you have to do analysis. Okay, so once you do that, okay, just explain. So you just put like that, you integrate, and so the idea, if you have this inequality, you integrate this with sine of z, and you integrate, and then you obtain this. You need to have here minus function, and you obtain this inequality. Okay, so actually this is my last slide. So maybe I could take 1 minute more. So you start with the function aij and take here plus minus 1. So this is the size, okay? The size. And this is just equals an a theta. And now when integrate that with respect to z that you have, then you have that this is this is a theta is equals an a times what we call Hadamard product anti-transpose of this one. And you iterate that, and you get this inequality that that this is true. That if you, so in other words, if you take this one, and you, instead of this, you take phi minus 1, and you do this one, this is how you prove the inequalities. But for Krivinin, Hadamard upper bounds, it is more complicated. So, okay, I finished on time.